Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Cyber Physical Systems, IAC. Today's talk is by Dr. Sounak, and he will be talking about delay bounds for quantum communication procedures under the repeat until success framework. Sounak is a postdoc at the LCA2 lab of EPFL IC. He defended his PhD thesis in October 21 at Technical University of Darmstadt. Previously, he obtained his bachelor's and master's degree from Indian Statistical Institute, Kolkata. He is broadly interested in analyzing network performance using tools from probability theory. Before we move on to the talk, we request the online audience to keep your microphones on silent for the duration of the talk, except while asking questions. And for questions, you may unmute yourself and ask Dr. Sounak directly, or you can wait till the end of the session. For in-person audience, we have arranged for high tea at the coffee hut, so please help yourselves after the talk. Over to you, Dr. Sounak.
Thank you very much. So, as the doc suggests, I will look into methods of obtaining delay bounds in quantum. Before I go into the details of quantum computing, I want to start with the rhetorical question: why at all? So, many of you might already know that there are numerous applications which are out of classical communicators or classical computers. And by out of each, what I mean is they are either impossible to solve by classical itself, or they are infeasible to solve like that. And the two examples that I quote here, one is from the realm of security. So, for example, by a classical system, eavesdropping detection on public channel is impossible. And the other one that I put here is about algorithms, where I'll take the example of the Deutsche algorithm from 1992, which solve a specific problem that is computationally interactive for classical problems. But to understand them deeper, we need to understand what is the quantum equivalent of a classical bit or a qubit, and how we can manipulate them to get them to do what we like. So, so the talk will follow this outline. First of all, I'll describe qubits in about 10 minutes, so that the details of quantum communication is clear to the audience. And then, as we all know, computing is only half of the problem. If we cannot move information from one place to other, then it's half baked, and that's why we need to look into the communication part as well. And quantum communication is really different from classical communication, so there are new challenges, and there are also innovative solutions to those challenges. And as I mentioned in the abstract, that quantum hardware for communication or even computation are really in their nascent state, and that's why we are being able. And that's why we need a spatial framework that was introduced by Elkouss, and it's called repeat until success. So we are not really looking at the delay for one attempt, but the delay until we succeed. And then using this framework, we look at something called to help us certain examples. So first of all, what is a qubit? A qubit is the simplest possible quantum mechanical system, and quantum mechanical system is an object that is governed by the postulates of quantum mechanics. And like a classical bit, both the mathematical abstraction and the physical quantity are called qubit. I will not go into the details of the postulate, but I will just briefly mention what they are about. So first of all, the first postulate is about the formalism for a closed quantum mechanical system. The second one is about the evolution of a closed quantum mechanical system. By closed, I mean there is no interaction with the system, with environment or outside. The third postulate is about what we can observe about quantum mechanical system. So this is contrary to postulate 2. So when we observe, we interact with the system. So this is not covered by postulate 2. So postulate 3 will tell us when we do measurements what we can really observe about the system. And postulate 4 is about finding the composite system from component systems. So let's look at the formalism for a qubit. So or a quantum mechanical system. So a quantum mechanical system state is given by or described by a unit vector in a suitable complex vector space with dependent problem. And this formalism does not really tell us about the exact state space or what is the current state of a qubit, but it tells us that there exists a complex vector space which will describe this describe the state of the system. So what is qubit? Going back to our original question, a qubit is the simplest possible quantum state, which is a unit vector in C. So the way to represent it is using the Dirac's notation. So it is read as get psi. The semi-angular brackets is read as get psi. We can see that it's actually complex vector alpha and beta are complex numbers, which satisfy the property that it has to be independent. So the amplitude sum of the one. And they are called probably amplitudes, which we'll see in a minute why this is the amplitudes. But there is a important further simplification for the issue. So if a complex vector satisfies the relation, I mean, if it's a unique complex vector, then it can be shown that the representation, the possible representation of a unique complex vector is like this. And one important point is the leading factor is called the global phase. It has no real observable effect. Or alternatively, if I say if I measure two qubits which only vary by the leading factor, then when I observe them, I'll get the same observation. So if I observe them 100 times, the distribution of my observations will be the same for them. And also for the evolution of the system, it's likewise. So so basically the first expression can be by what I have this kind of. And yeah, one more important point is that the vectors 1, 0 and 0, 1, they are special unit vectors in this representation, and they are called computational basis vectors. The first one is called 10, 0, and the second one is called 10. I will be using these notations. And then the important question: how we can realize a qubit? We recall that a classical bit can be realized by any physical system that exists. States, for example, levels are the most popular realization. Likewise, we can have qubit realization by any physical system whose state space solve the unit complex vector space. So the most famous or most popular example is polarization of but there are other realizations as well. And it is important to note that most of these realizations require cryogenic temperatures. That's why building a quantum computer is very different. But there exists some realizations which work through temperature as well, but those are expensive. Yes. Another important point here is although we see that realization is about a physical system whose state space exalts the entire complex vector space, suitable unit complex vector space. We can only observe few states when you observe the system. So it's not the entire uncountable space that we observe. Our observation is usually finite or countable. For all the examples I did, they are mostly finite. So I have been talking about measurements. So measurements is about observing a quantum mechanical system. And as I have already said that when I observe them, I can only observe finite number of quantities for the examples that is there. So formally, those outcomes will be denoted by the index small n, and corresponding to each outcome or each measurement outcome or each observation, I will have measurement factors. And these the set of measurement matrices will satisfy this completeness relation that see towards the top of the slide. So that is the formalism for measurements. And when we measure in that basis, so in the basis corresponding to this set of matrices, then what are the outcomes?
Sorry, it's lost over. Think about it.
Yeah, please.
So this is fine. Don't have, yeah. So what you know, like yeah, slide 7.
Yeah.
So what do you mean by the you're talking about measurements, right?
Yeah.
So when you say measurements, then you're giving me matrix. So I'm a bit confused. So suppose I had a. So let's not talk about quantum. Let's stick with order compound. So it was trying to, you know, like observe an experiment, right? And say it's a coin toss, right? Then I get to see one of the two outcomes, right? So it'll be a bunch of scalars which I'll observe. Okay. So what I'll do is maybe a random outcome, but I know where this set belongs to. What these matrices are now, I'm not sure. So what you explain a little bit more?
Yeah,
Or observations are.
Yeah, sure. So I'll take example, but I think just to explain what I can observe. So I'll take example of this. So let's say your qubit is in the say that's fine.
So what is clear to me, qubit is a unit vector. Qubit is a unit vector in C2 or all unit vectors in C2? How do you define?
Qubit is a unit vector in
Qubit is unit vector. Now what do you get to observe?
So when you observe this xi, so it depends on the basis on which you observe on your experimental setup, but you will observe either 0, get 0 or get. So that's what it is.
So I don't quite understand. So you will either see one unit vector or it's optimal unit vector. That's what you can see. That's
Yes.
it. One or the two.
Yes.
But then you actually said that your qubit is actually could be a combination of those, right?
Yeah. So you cannot observe that. So you cannot
get a linear combination. You only get to see one or the other.
Yes.
Okay.
So they exist in a superposition of these two states, but at the moment you measure it,
You only get to see either one or the other.
Yeah.
Okay. Moving on then.
so you can do it in different bases. So the example.
So again, I'm not getting a basis, right? So the way you said that you get to say get 0 or get 1, that means you already told me a basis, right?
Yeah.
Are you saying there are other bases on which you can observe as well? One of the.
Yeah.
So you're saying, so suppose now you're talking about C2, but suppose you're talking about CK. Because when you say basis, that means you're assuming there's a K dimensional space, right?
Exactly.
And then for any K dimensional space, there is a K dimension, K basis, right?
Yeah.
Not be unique. One of the bases is what you observe.
Yeah. So so that depends on your experimental setup. So for example, you can make an experiment where your observation results will fall into either of these cases.
But you know, like I don't quite understand. Like the basis is something which you can always change, right? But
Yes.
the experiment observation should be independent of what I choose to be as the basis.
No. So your experiment,
Like just this doesn't make sense, right? I mean, I just 0, 1 and 1, 0 is in your mind, right? There is no 0, 1 in the world, right? I always shift it and this becomes another basis. But experiment observation will be experiment observation. This should be nothing with the basis that defined.
yeah. So let's take the example of an electron which can exist in the high energy state or the low energy state. So whenever you observe it, it will either be 0 or 1. So 0 probably.
So
0
you're just following that view.
Yeah, we are calling the low energy state 0 or the high energy state 1.
Okay.
But you can make some transformation in your experiments. So probably for the electron there does not exist any other meaningful basis, physically meaningful basis. But for other experiments there could be physically meaningful basis as well. And you can make your experiment outcomes suited to that basis.
Oh, okay. So forget about that. That's become. Let's stick with this. Suppose I'm one basis. So now can you tell me what is this matrix?
Yeah, sure. So then I think I'll jump one slide and look at the simplest possible measurement outcomes. So this is called measurement in the computational basis. So here the matrices will.
Okay, I'm a bit. So your observations are M0 and 1, or what is your observation?
No.
What is M0 and 1?
No, M0 and M1 are the measurement matrices.
Okay.
And your observation will be 0, 1. So outcome is observation.
Okay, and what are you calling 0 1? I thought you were supposed to be vectors, which will be your outcomes.
So to be specific, so 0 and 1 they are actually the indices. And
Of
they
the one of the bases. Because you have two bases, you call them.
exactly.
So, see, for people who are uninformed and quantum,
Okay,
like,
can I
it-
explain if you don't mind?
Yeah.
So it is basically any qubit can be done if we are in C2, suppose we have a basis say x cat and y cat, then any qubit can be written as a linear combination as alpha time x cat plus beta time y cat. Then according to the law of quantum mechanics, postulate of quantum mechanics, when we are going to observe it, we can't get alpha and beta. That's the rule. So what we are going to get is, we are going to get is mode of alpha cat or beta cat answer with the probability mode of alpha square and mode of beta square. That is the rule. So it's a postulate of quantum.
More great question, he is answering it correctly also. So M0, M1 is something which you designed, right? And so I think what would have helped that you know tell that 0 is correct, corresponding to the vector
Yeah, exactly.
0, 1 and
So,
1 corresponding to.
yeah, I have that to the right. Okay. So basically 0 corresponds to the vector get 0, and this is actually get 0 because they differ from get 0 just by a global this factor, which I have.
I mean, like the sign.
Yeah. So it's just a unit modulus complex number. So this is get 0. Yeah.
Sorry, I'm asking.
No problem. It's meant to be a discussion. So yeah.
7, not 5.
Okay, 7.
Yeah, because you skipped that one to explain to me what is that. See, I'm sure the other students also have questions. They're just too shy.
Yeah, and feel free to interrupt me whenever.
Yeah. Okay. Now, please go ahead and explain it.
So yeah. So what I'm saying here, there are let's say m experiments. Let's say so I have mixed up the index here of it. So probably k and m remain the same. So they are the indices. They are the running index for the possible outcomes. And if there let's say there are n possible outcomes, then there will be n measurement matrices corresponding to.
Okay, so this hang up for here for a minute, right? So as you said, this part I'm not getting. So suppose you have basis k, right? And as you just said that I cannot, and your outcome should actually be linear combination of this k basis vector. So
Yeah.
E1 to ek or
Yeah.
alpha 1, whatever. So then you and actually you only get to observe one of them, right? But
No, not really one of them. You
only one of the basis you said, right? Only one of the basis you get. That's what you said. I didn't say.
once.
Huh?
So if you
Right,
write
at once in one observation, you only get to observe
yeah,
one.
exactly.
Second time you observe, you probably get to see another one of them,
Yeah.
right? And so actually your possible outcomes are, I mean, just these the basis, right? The dimensionality of the whatever
Yeah.
space you're looking.
Yeah.
Okay, and then what is this measurement matrix doing? This part not clear.
So you can relate every outcome of your measurement to these measurement matrices. So you don't know. So you don't exactly know all the possible bases, right? Your experiment outcome could be in any possible basis, and corresponding to that base, you will have a set of measurements.
Not zero understanding what it is.
Okay.
Are you guys
that's-
clear? I mean, maybe I'm the only one studying.
It's basically mathematically what we are doing. He's trying to say that experimentally.
No, mathematically also not clear
Yeah,
what
so
you're saying.
mathematically, if you have a qubit and when you are going to measure them, mathematically what you have to do, you have to apply these matrices and you are going to get answer as one of the computational bases with the probability mode of alpha square first and mode of beta square as second.
So
That's what-
let us take the example. Let us look into the two examples that I have.
Right.
So I think the first example. So let's see what is this example.
Depend upon your computer.
So get started with alpha beta. I'm going to measure it and in the basis that corresponds to these matrices. If it's not
How do you design this for? Like why did you come with design 0 and M1? When I just see bunch of zeros and ones, only thing I can see that M0 has
so that's
your
because,
one of the bases in M0 and one of the bases in M1, and other column is set to be.
that's because I know the possible outcomes. So I know the possible outcomes to be get 0 and get 1.
Okay.
And corresponding to those two possible outcomes, what are the measurements? So it's like working back from here. But having the possible outcomes is only half of the story. I also need to know what is the probability of these outcomes.
I will go to first. I want to understand how you design. How do you design this measurement matrix?
So it's
only
coming from now.
So let me say this and correct me if I'm wrong. If I have a k-dimensional unit vector, right? That's the output going to be. Will my mi is going to be just one unit vector and then all zeros columns? Is that what it's gonna be? Because this is what you're suggesting right now.
Not always. So that's what I have in the second example. So,
So what is the condition in go back? So because okay, what I'm not getting is that what do you apply this measurement matrix?
So I do not apply the measurement. So for experiments, I do not apply any measurement. For experiments, I just
Why do you have this measurement? I do not
yeah,
understand.
it's just a formalism to tell you what are your possible outcomes, which you already know, but you do not know the chance or the probability that you will see these outcomes.
But if I don't know, then I would even not know where this measurement matrices belong, right? The formula is not clear to me. Like if you do not even know the dimensionality.
No,
They are these dimensional operators. Amen.
possibly, but I'm only looking at the final.
But then in the formation, then you already decided that my basis is limited to the dimension of the dimension, right?
Of course, so there cannot be, so there will be exact aspects, so if the dimension is A, then there will be exact.
Okay. So then this is your first condition for whatever some watt per second reason we
Yeah.
be high. Okay.
Yeah.
And what is the second thing?
So the second thing actually tells you what is the probability that you observe one. So one of those basis vectors, what is the probability you observe at the end of the experiment that is.
So what is bothering me is that somehow you're saying the probability of my observation depends on my design, which is I don't understand that.
Yeah, it does.
If I was if I was a stupid, I designed some very bad measurement methods, then why should the law of physics follow my my design?
No, it's not only laws of physics, it's also your experiment design, because I mean, so basically these basis vectors they will so for example so let me go to the second example, then I think a lot of things will be.
Okay, this first example was also not clear.
Oh, okay,
Completely.
let's be
Yeah, so this is clear that this is some of our entity here.
Yeah.
Okay. And then
and then I know the
so what do you mean by input state?
so we measure this. Get psi is the quantum state that you are going to measure. Okay. And then when you measure it or observe it, it falls into one of these states. It's equivalent to 0 or at 1. And the probability with which you are going to observe at 0 is mod of alpha square, and the probability which you are going to observe at 1 is mod of alpha square.
I understand your calculation, but I don't understand anything else. You just gave me a definition and you asked me to do it.
Okay, so you
So no, I mean.
No, your calculations are correct. I
Yeah,
checked, but I don't understand.
What is the question?
I'm also not clear what is going on. Like you're saying that I'm going to have an input vector alpha beta, right?
Yeah.
Which you don't know, and you say that I'm going to multiply the m0, then I'm going to get alpha squared. Because that's clear. So what? What is the point you're making? I don't understand.
The point I'm making is you can make measurements, and what is going to be the distribution of those measurements. And this is I mean, you can probably use this to differentiate between two states, for example. So if you're so for example, if your qubit is in state 0, then you are never going to observe that, for example, when you measure. You will always observe.
You said this again. That's not the problem. I guess I think something which is obvious to you, which is not clear to me, and we're not able to communicate with me.
okay, so you performed experiment and the output state is what you get in your outputs, and you're showing it that what is the probability? You're showing that mathematically how you get it, right?
Yeah, exactly. So what is?
But then, like, is that postulate you're following? That's what you're saying, that maths comes from.
It's from the postulate, but I mean, why is this useful? That is something.
One of the uses, like, suppose we are doing quantum error correction, and if some error has happened and we want to correct that, so we can't do
Forget
classical.
quantum correction. This is not.
Yeah, so that's what I'm trying to say. Is if you want to look at what is your state now, you can't know what is alpha and beta. So what you can do is you do the measurement and you can know. Okay, now the answer is 0 ket with this
No, but
probability.
it seems like you seem like you're giving me m0 and m1, and then any observation I'll be able to tell you p0 and p1. So what is left to do? What is not known? I mean, maybe something you're not telling me.
Okay. So I mean.
No, I will not know in P0 and P1. This is just the probability that I'm going to get 0 ket.
Are you presenter or go work? I mean, who's speaking? Who's presenting?
So
You are presenting, right?
so I think why are these problems? Right?
Yeah.
That's your question. So
No, so it seems like if there was alpha, beta was your vector, right? You can
so
apply.
I do not know alpha and beta.
So you do not know. Very good, right? But you know M0 and M0, right? M0, it seems.
If I know that the outcomes are get zero,
No,
and
let me
M1,
ask M0 and M1 you know, right? Or you don't know.
so in this case, I yes.
Yeah. So if it seems like you apply, this M0 to your side and you can measure that, then you get T0 T1 right away. What is the question here then? Or what is unknown? In this problem, what is unknown? What is known?
Yeah, the unknown is
So unknown is alpha beta, you told me. But it seems like if I apply M0 to psi and if I'm able to observe that, right, then I take inner product with itself and I'll get alpha square, no?
yeah, the unknown is if I
Do I get to see M0 into psi or no? M0 applied to psi, do I get to observe or no?
yes, M0 applied to psi is get zero. That's what
Do I get to observe that, right?
yeah, I do
But
get
if M0 is psi, if I get to observe it, and if I get to observe that vector, then I take inner product with itself, then I know alpha right away, no? And M1, if I get to observe M1 inner product with psi, I take inner product with itself, and I get to observe beta. What is left to find out?
no. There's a catch here because M0 times psi, that is not a unit vector. So you do not exactly know M0 times psi. What you know is M0 times psi pi square root of T0. So there is a normalization.
So you get to observe M0 psi divided by whatever the normal is. That's the only thing you get to.
Yeah.
So now the question is basically how do you get alpha and beta? That's the question. Is that the question?
No.
What is the question?
So the question is, if I observe a quantum mechanical system which is in the state sign, then what is the distribution of your observation? That's the question. So it's not a problem. It's a theory. So the theory says when you observe a qubit, it actually falls down to one of the DC states with certain properties.
And those properties you know, you don't.
So if you do not know alpha and beta, you do not know.
Okay.
But you can estimate them if you.
And how do you estimate them?
So if
So
you,
that is the problem, right?
yeah.
So how
So
do you
if
estimate?
you want to estimate them, if you have a perfect mechanism to create identical qubits over and over again, then you can run the experiments many
And
times.
when you say identical means like the same problem.
No, the same qubit. That is not easy. So just making the qubit get signed. So the same qubit experimentally, it's not easy to make the.
Is
same
it
qubit
possible
over.
even due to not knowing? How can you
Sorry?
get, how you are going to get psi and copies of psi? It's not possible because of no.
No, you are not going to make copies. So let's say you know. So let's say you are not making copies here, right? So I'm not making copies here, but I have a mechanism to let's say to produce a quantum mechanical state over and over again. So I'm not making copies.
Then you are not going to get exactly psi every.
So it's experimentally difficult. That's what I said. So, but if you have the mechanism,
So according to your theory, then writing all of this is nonsense because you're not going to observe it. So what is the point of writing it? Because this gives me false sense of that I can actually find alpha and beta.
no, it is not because it helps me distinguish the state. So, for example, if let's say my algorithm depends whether get psi was 0 or 1. I want to check.
Okay, so this is what let's move forward. What I only observe is that your actual state is gonna be a vector in C2, but you do not know what it's
The amplitudes are
you do not know the how do you say it? It's can be written as a linear combination of your unit vectors, but you do not know what the linear coefficients are, right?
Yeah.
And your observation is gonna be one of the unit vectors. That's all I understood from your talk so far.
So far, yes.
Okay, let's look at the second example.
Yeah.
Very good.
So this is the second example.
This is what you have designed.
Now, this
I mean, like somebody would have designed, give you like this is your measurement matrix, and then you get to observe.
so you can work them back from the output states, so the observations.
I'm a bit lost. So what you get to know is what are the possible observations. Is that what you start with?
Yes.
Oh, wait a second. So then, but what you observe depends on what you apply to it. No. Transformation isn't what.
So there is a one-to-one correspondence in experiments. This is what you observe, and from there you can design the measurement. So what I'm saying,
Okay. So let me go on. This measurement matrix is just a modeling tool, right? There is no measurement matrix in your form. There is no reality. There's no real
it's
measurement matrix.
yes.
It's just in your head. There's a measurement matrix leading to this out, right?
Yeah, exactly.
Okay.
So so if there So we can also make the measurements in a different basis. So for example, this is called get psi and this is called this is called get plus and this is called get minus.
But why do all the distinction? In the end, you are just observing one or the other. Why not just call it 1, 0? Could be 1, 1 or 1, 0, and it's the same.
Because this is different from 1, 0.
No, it's the same, on some other basis. Like, why such so special that 1, 1 and 1 minus 1 is different than 1, 0, 0, 1? To me, it's the same. As long as there are orthogonal there.
So one direct answer.
Because they're also orthogonal, they're unit vectors. What is so special about it?
Yeah, because if you look at the distribution of the outcome, then it's different. So it's not anymore.
Yeah. But who's to tell you that what is the most fundamental? So someone in your mind, there is an actual basis in which you want representation.
No,
because this is just transformation of basis, right? What you want is that it's just So who told you that? So it seems like there is a real basis, and you get to observe in some other basis. It seems, right?
Yeah.
And and what is the real basis? I mean, you would never been able to get to observe it.
So
right, because somebody telling that 1, 0, 0 was the fundamental basis for which I want to know the coefficients alpha and beta, right? And this is a transform basis,
right? But it's so 1, 0, 0, 1 is it depends on your physical realization, as I said. And this what I'm showing here gets get plus and get minus. They also might have some physical representation. For example, so it's like
okay, fine, I will. No, I yeah.
Okay, all right. So yeah, so I think I have one more examples as to why these measurement outcomes or the distribution of measurement outcomes is important. So I'll take example of one algorithm where it will be more clear. So but for now, so what I want to focus on is on composite systems. So if I have component physical systems where I know the state spaces, then the component system is just tensor product of the individual state spaces. And if I know the exact states, then to get the final state of the component system, I can and there is some simplification of notation. For example, so if I just attempt to get notations, it's actually the tensor product. And then the second one is a new notation which is called bracket. So it's just the inner product of two vectors. So it's basically psi conjugate phi. And then there's some expansion of the possible states in C4. So in C4 we'll have, so if we have a 2-qubit system, we'll have the corresponding system will be in C4, and the computational basis in that case will be these 4 vectors next time condition. So another example of composite system.
So just one question.
Yeah.
So it seems like the your measurement matrix are the one which will transform from one basis to another, or is it what is they going to do? Because you observe certain bases, right? And you're saying maybe those are not the bases in which the original qubits were, right?
No, so there is no concept of original qubits being one basis.
So you wrote this alpha beta, no? So okay.
So I chose one basis. So it's all in my mind. So there might be some physical limitations.
So then basically you can always assume that whatever I'm observing is in the right base. This is the base, right?
Yeah, you can say so.
So then why, what is so special? So why did you show me 2 different bases? How are 2 different examples different?
So that is I will take some examples.
That is otherwise just a transformation of bases, right?
Yeah, it is basis. So it depends how you apply them, how will you take advantage of this.
Okay, fine.
So the first example here is just making looking at the composite system. The second example which is here, so get psi is given by this representation. So we can check that this is indeed a unit vector is 4. That's why it's a valid state for a 2-qubit system. But this state cannot be factorized. So like we have a factorization first out, it cannot be factorized. So when a state cannot be factorized, then the state is called a derive, which is a crucial element of quantum computation. So we'll see more examples of this.
Let me go back for a second.
Yeah.
So you said C2 I can go to C4 by doing this outer product,
Yeah.
tensor product.
Yeah.
And then of course these are only giving you some basis. These are giving you basis, right? So there is many which will not be able to be able to characterize. So that's not the only example, right? Just
Yeah.
There'll be many such examples.
Yeah.
Next.
So yeah, so the point here was if I know the component system, I can go to the component systems, but not the other way in general.
But what do you mean by correlation? Correlated? You're saying correlated.
Yeah.
So you're just saying that it is. So here, for example, you've written as those 0, 0 and 0, 1, right?
On the go,
Now this one psi.
the size is 0, 0 and 1, 1.
0, 0 and 1, 1, correct, right? And the other one was 0, 0 and 0, 1.
Yeah.
The sum. So I'm a bit lost though, right? That composite system is a bit confusing because the plus itself was not unit vector in the original unit, right? The plus itself was not 0 or 1, it was a linear combination of 0 and 1,
Yeah.
right? So why is that not an entanglement? Why is this an entanglement? Because there's something special you're saying.
Yeah, right. So if I can express them as product of two C2 states, then it's not intact.
Okay. Got it. So, for example, what can you write it as? Like if if you mean this so.
So if I
Yeah, no. So that what is bothering is the conflict. Okay, maybe it's 0 is the conflict. I see. So see, anything which is in C4 can always be written as a linear combination like this, right?
so of four like this that I have.
Right. Anything can be written as, but you see that if there is some commonality, then you can write the tensor product. Like for example, in the first example, you had the 0 in the common, and then you took it out, and then you call plus as 1 by square root 0 plus 1 by square root 1.
Yeah. So there is another example. So it's often written in the literature without normalization. So we have to normalize it, re-normalize it, and this is the actual state. So it's a valid unit vector in C4. So we want to check whether this state is entangled or not. So we can prove it by contradiction. Very simple. So let's assume that it can be done. And then from the expression, we see that if one has to be 0, then at least another vector has to be.
Maybe 0 in either 18 and or 2.
Yeah.
Boss.
So this is
Sorry for humoring me, and I don't know about others. Thanks.
yeah, and then there is the last postulate, which is about evolution of course system. So it tells you that the evolution, so the nth state and the state at the beginning are related by a unitary transformation, which is dependent only on the start and the end. And this actually helps us design the classical quantum equivalent methodology text that we see in the classical world. I'll just give you some examples of these quantum cases which are given by such unitary transformation. So yes. So the quantum equivalent of not gate is what flips the amplitude. So you start with get sign, and then so you have other times get 0 plus b and it transforms it to other like 1 and the corresponding unitary transformation is given by matrix called index.
How do you implement it?
In reality,
Yeah. Take one of your favorite quantum examples.
so I have to check about the physical implementation.
Because I mean, like for classical technical signals, it's quite obvious, right? But here it's not clear.
Yeah, so I have to check. And then there is another quite frequently used gate, which is called the Hanamari. So what it does is it changes the state get 0 to get plus, and state get 1 get minus. And there is a useful notation for the Hadamard gate, which I'm using so far. So you can just plug them in. So you can just plug that 0 and 1 here and verify that this instructions.
Sorry, I don't know again what is the last point you're trying to make in this edge? Or you just say this
So
formula is
yeah,
correct?
I'm just representing here because when I look at composite systems, I'll take the multiplication of different Hadamard gates, and then it's useful to use the formula. So
The summation Z is over what? All possible.
all possible unit vectors. So all possible bases here. So it will be here over here 0.
I mean, these were just showing for 2, but you're actually thinking of Hadamard in much higher dimensions. So, right?
No, this is only for 2. If I do it for higher dimension, so there will be, I mean, there will be similar
formula. It's a different number.
So yeah, I think now we have I have covered the basics of the qubit, and now I just want to take example of one algorithm which shows why the quantum the example is Deutsch algorithm from 1992. So what is given to us is a matrix computer which implements a function from 0 1 power n to 0 1. And it is given that it is qubit constant, so it is either always 0 or always 1, but it is balanced. So it's exactly 0. It's 0 for exactly half of them and 1 for. And what we want to determine is whether it's balanced or not. And for classical algorithm, it requires k queries to check this. So we can check that if it's balanced in the best case, if it's balanced and you query it 2 times and you get sorry. So yeah, so if you query it 2 times, you get 2 different outcomes and you know it's balanced. So that's the best case. But in the worst case, you have to query at least half of them plus 1 to get whether it's balanced or not. And for quantum algorithm, it's just constant. So that's what I'll show here. So first of all, I start with the specially designed quantum state. So which is 0 power cross n. So which means there are n qubits at the state 0 and 1 qubit. So there are n plus 1 qubits. 1 qubit in state 1, and then we apply Hadamard on each qubit. So if I apply Hadamard on 0 power n and I send this formula, I can it's not much calculation. It's that the first will be like this, and the second one we know directly that if I apply Hadamard on 1, it's get minus. That's what I have. So in the next step, we apply this transformation. So from x here is 0 power cross n and y is 1. So we make this transformation here. So it's just so I retain x and
No,
then
I didn't get it how you. Somehow I have to relate it to your hx, but I didn't get it how you teach it.
the first one.
First step, yeah.
Yeah.
You are giving me the formula of h, like I don't apply to x. How is that translated?
So it would be so you apply individually. So you basically do is you take you multiply them over so this will be this power n. So it will be tensor product of all of them. So
All of them in that sum.
yeah. So this one cross product the same thing, cross product the same.
But that's something h Hadamard applied to x is not 0, right? Somehow you have to take the right x so that Hadamard multiplied to x is equal to 0 because you're taking 0 tensor product n times, no?
Yeah. So I'm applying Hadamard individually to each qubit.
Each 0
It's 0 and 1 as well.
in the last one. And why you do that?
I mean, because that's
So
what
what is why the input? I don't understand. So I understood your original question. I don't understand what is this input you're doing. So You're telling me that I took some input which is n times tensor product of 0, then 1, and then you're trying to add on all of them. Why are you doing all
Yeah,
of that?
because this will help me answer the question in this one.
All right, let's continue.
So so I mean it's not easy to think of this state. So they wrote a paper out of this. So basically I apply all qubits and then I apply this transformation, and then what I can do, I ignore the last qubit and then again apply Harman on this.
I can understand this problem. If you want, you can explain or you can move on. I think get it.
So ignore this one here and apply Harman on this. So if I do just h time x, so I already have -1 for fx, then I do h times x and I just plug this. So the second sum is over z, and you have -1 for z. So it's -1 for z plus. It's just plugging in what I have.
Can you say in English? Forget all the math. What did you do and what did you get?
Okay, so
Because I cannot do this calculation.
yeah, of course. So what we're trying to do here, we are taking a special input state and making it go through certain transformations, and in that what I will have is if f is balanced.
So we need, okay, so state. So initially when you had that function go back 0, 1 to the power the previous right, and here what is your input state for this quantum thing? It's not 0, 1 to 4. So this f, because this f, what does it even mean? Because you don't have any more scalar inputs and scalar, right? In quantum world you're picking up vectors, right? See this vector, I understand what this vector is doing, right? So this function you give like 0, 1, and it outputs 0 or 1, right? And then you just want to check whether it's function or it's balanced. Right? And in there, what is your input? Your input is vectors.
So
you're giving like this zeros are from C2, right?
Yeah. Just 1 second. So yes. So I mean, what I want to say here is it's a quantum equivalent of FC1. So zero is
So what would be balance or constant here? I mean, here is it that you give whether 0 or 1 of those, and then you'll only get 0 or 1 as well.
Yeah.
That's what you're thinking, right?
Yeah.
Or if it was balanced, then you will see half of 0 then half of 1 as well.
Yes.
That's what you're thinking.
Yeah. So I just replaced 0 by F0 and 1.
Yeah, exactly. Now what are you doing? So
yeah. Now. So
see, if you leave this thing, now you're not clear.
Yeah.
We are not okay.
Yeah.
Next time.
Yeah. So and now I end up with this thing for the first n qubits.
No, I'm not understanding, right? So I understood your function now, f, right?
Yeah.
Now and this input now is clear. We both are thinking. Now what you're doing, I'm not clear to me. Now you're saying that instead of giving input, I'm giving some other input by applying Hadamard transformation to it, or what is it that you're using? Apply Hadamard on each qubit. What does that even mean? Or the output you're gonna change by applying Hadamard. What are you doing?
No, I'm starting with the input state.
Okay.
And then I'm applying some transformation on that state.
So why have you taken this inputs?
Yeah, because this will lead to a special state where I can make some certain experiments, which is very clear. So that is the next step actually. So I think let me tell you the next step.
Okay.
And then let's see whether it's clear. So if we look at the amplitude of 0 power cross n, then that will be simply so when it's all zeros, what we have here. So the first term, so -1 power x z, that will be 0, so it will be -1 power x.
I mean, don't worry about it. It's not like you can parse it. So just whatever you want to say, just say it.
Yeah. So so basically what I'm trying to say here, so if you look at this, then it is either, so the amplitude of 0 power cos n is either plus minus 1 or 0. So it is plus minus 1 when n is constant, and it is 0 when n is balanced.
Okay, so
So if I measure it in the computation basis, then either I will observe only 0 or I will not observe 0 at all.
okay, so you're saying that I can, so please summarize. So you're saying that I can design a special input. By looking at that output, I can tell the response to the balance.
Yeah, exactly.
Where there at but I could have designed a good input just now. You do not know F here. So you're saying regardless of what F is, this is what's gonna happen.
So not regardless, I'm satisfying those conditions. So F has to satisfy these conditions. You do not know.
No, I understood. Here there is no way you can design input which you need to get out, because that's what F is gonna do as unpredictable. So F is somehow being given by an adversary, and you cannot do anything. So I did not get the intermediate, but okay.
I mean, the point is you have a special input and some special transformation so that the output is something that helps you discern between these. Okay. So that was about some fundamentals, and now I want to talk about the computation part. So the basic challenges are these. So quantum states cannot be copied, so it's given by the no here. And then the length distances over which they can travel, it's very low. It's not like the telecom. And then the quantum signal cannot be directly amplified, so it's also very hard to achieve that. And then again, as I said previously, qubits are fragile. They interact with environment, and they and if they interact with environment, they become noisy and they are not useful. And the solution to these two problems, so for single hop distance, if I want to do it, what I use is teleportation. And if I do it over multiple hops, then what I do is called entangled swapping, which is a standard method. And I'll explain what teleportation is here. So what I have is a quantum channel. Quantum channel is usually an optical link or free space, and that exists between the sender and receiver. And I also need a classical channel for sharing necessary information during this technology. And the third thing, which is the actual quantum resource, is shared entangled. Is called a bell pair. So what is a bell pair? That is written on the second line. So there is a typo for B there, so it should be in the suffix. So it is called get 5 plus. So this is basically 0 0 and 1 1. So the entangled state I can example of. So that is my entangled resource. And
so can I ask a question?
Yeah.
So I don't understand the communication aspect yet. So my assumption again, I'm assuming that your information is in the two vectors, unit vector 0 and unit vector 1, right? Or your information is inside. Which is
inside, yes. So this is my data feed.
This is the which has alpha and beta, which are also unknown. And now, when you communicate, what do you receive? What do you receive?
I will receive
5 plus. Is that what you mean?
No, I will receive. I will receive this. So A has get psi, and B will, at the end B will have get psi.
Okay, so you're saying that A has get psi and B will receive get psi. So then where is the noise coming? There's no noise. People can always receive the qubit correctly.
No, there is noise, but I'm looking at perfect example. When everything is perfect, how is it done?
Okay. So even if you receive it, you're not able to decode alpha and beta, right? So this is then what this information is useless.
No, it is not useless actually.
Okay.
So I mean, if I look at alpha and beta, if I try to look at alpha, then it will become useless actually, because then I destroy it.
So then how is information being transferred?
So the qubit itself is being transferred, and I might use it. So for example, so in the previous example, I said that for example, it could be get psi, it could be psi plus. So I want to transfer that to the other end. So I mean, in general, I do not do Is it
And what is this bell pair then?
Yeah, well, there is this entangled state in C4. So this is 0, 0.
Yeah, you just gave me one time of what do I do with? What is the point?
Yeah,
of
the point is this bell pair. When A and B share some entanglement, then only I can then only in the known ways, then only I can share phi C from one to the other. Because I cannot copy phi C. Or I cannot observe it. If I
You're
observe
saying
it
only if you have this, then you'll be able to transfer.
in the known ways.
Fine. And then what is the third thing? Composite state.
Yeah. So the third thing is the composite set. It's just tensor product of what I have in the first set.
Psi C and phi plus.
Yeah.
And if you take it, what will you get?
Now, so now what I have at with A. So what I have done here is I have actually expanded 0, 0 and 1, 1. So 0, 0.
What is the 0 A and 0 B? What are the
Yeah. So the suffixes are actually for the receiver and sender. A is the sender, Alice, B is Bob, is the receiver, C is the data feed. So A and C is with A in the beginning.
Can we go back to the last time?
Yeah.
So, data cubic A wants to send, I guess you're trying to say that you are not going to send phi C through a Barnum channel. And you're
Yeah.
going to use the
I'm going to use television.
classical channel.
No, I'm not going. I'm going to use classical channel, but not only classical channel.
And the bell pair, that's
Yeah.
it.
So basically, bell pair is shared between A and B. So let's say I have a mechanism where I can make two entangled atoms in this state, and then emit them towards two ends, A and B. So A and B now have the shared bell pair. So this is my composite set. So from the first line to the second line, what I have used is I can express 0, 0 and 1, 1 in terms of these four bases. These are 4 basis vectors. I have just 3 ends. So it's quite straightforward. So it's just I think 1 by root 2 phi plus phi minus will give you source. So you expand them and then you see what A has and what B has. And now what I do is I make a local measurement at A. So if I do a local measurement at A in bell basis, which means I use one of these base vectors, I use these base vectors, and then the observation will be.
So can I ask you a moment?
Yeah.
So phi plus you had told me, what is phi minus and psi
Yeah,
plus?
phi minus is 0, 0 minus 1, 1. Phi plus is 0, 1 plus 1, 0. Phi minus.
You think there is some recognition.
Yeah. So they are basically these are different bases for C4. And I make a measurement in that basis. So what I will observe is then basically what happens when I do the measurement, then the system collapses to one of them. So all
I don't understand that. What do you know local measurement and what is the mathematical operation you do?
it's the measurement matrices that I have.
So the measurement matrix was just pre-multiplying your side.
Yes.
So what is it you're gonna tell me what you're gonna pre-multiply? So this is your entire output, right? Now you're gonna pre-multipy with this another matrix,
Yes.
and you're gonna say you're gonna pre-multiply one of these 4 matrices because they are orthogonal to each other. Is that what you're gonna do?
Yes. I'm going to pre-multiply with one of them. So
phi plus for example.
yeah, let's say I'm going to pre-multiply with the measure of phi plus. Then what I will observe in the end, it will be only the first term.
Correct. Everything else will go disappear.
And then what I know is at B's end, I'm left with what I left with the data. So if I observe phi plus, but if I do not observe phi plus, then I observe something else, not exactly the data field, but some transformation, and so on. And now what I'm saying that via classical channel, the local measurement outcomes are communicated from A. And according to that measurement outcome, we can apply a transformation. So for the first case, we does not need to apply any transformation. For the second case, if we apply Z transformation, which is something like X, then it will become the data itself, and so on.
Okay.
So this is how the information is passed on to me. Okay. And then if the distance is not good enough for transmitting the bell waves, then what we use is repeater. So again, there is a quantum channel here and a classical channel. So what we
So can I again you ask the question? Go back. So this bell pair is what you were using to transmit, right? Is this classical channel or quantum channel? Don't know.
bell pair is transmitted by quantum channel.
So then what is classical channel mean?
Classical channel is used to give me the measurement outcome. So whether you observe 5 plus 1 minus psi plus or psi minus.
How do you know? I mean, I don't understand this.
So A makes a local measurement, right? So the measurement outcome is any 4 of these. And A has an apparatus which tells.
Now, what does it mean that A makes a local measurement? What does it mean? Thank you.
So you mean mathematically or
Yeah, mathematically. What does it mean?
mathematically you already told me that it's pre-multiplication by.
So that's what you mean by, and that is a classical channel. That's what you're calling.
No, this is
I don't understand.
no measurement. Local measurement is done by the quantum apparatus, and then it is transmitted to B via classical.
Oh. Oh. Got it.
So now when we have to reach for distance, then I cannot share the bell pair between these 2 nodes, so I have a repeater in between, and the steps here are as follows. So first I have links established between A and R. By link established, I mean A and R share bell pair, and then this can be run comparatively. So A and R share bell pairs. And in the next step, what I can do is I can do an entanglement swapping at R, which makes a integral entanglement.
What is entanglement swapping?
So this is something related to teleportation. I have not included the details. So it is something.
Go back. So I understood this sharing of bell pair between AR and DR. I understood.
Yeah. So what you will do here, you will have 4 states. So here you have 3 states. Sorry, here.
See, instead of you having A and B, you have AR and BR. So you probably
So you will have AR1, BR2.
Right.
And from there, if you make a measurement at R1, R2, then you will end up with. That's what.
Okay.
Okay.
So we're exceeding time. Is it okay for you to wrap up?
Yeah. All right. So I think we are only in the beginning. So what I wanted to talk about is actually that these experiments, they are actually very and the hardware does not support them to be executed all at once. So to give you a sense, they can be executed. So if you execute them from, let's say, 100 to 10,000 times, then it will be success. So
what do you mean by succeed on? It seems like there is no problem, right? Every time you transmit, you're successfully able. So what is that failure here?
Yeah, the failure is so when you so let's take an example of.
Oh, you mean you're not able to do this? The sharing is not you're not able to do. Is that what you say?
So when you transmit the photon, so usually it's done from midway to A and R. So you produce 2 entangled photons and transmit them to the photons, and then they cannot be detected.
Okay. And you're saying, so this is what you call failure every time undetected. So you have
the failure in the simplest.
And then you keep transmitting it till it's received.
Yeah.
That is what you call repeat and success. Okay.
And also in the second step, when I do an entanglement swap in R, then also there is a failure. So in the first case, the success is constant, so it depends on the hardware. In the next case, I see that there is difference between the times these two bell pairs were made available to R. So AR probably succeeded a few minutes ago than BR succeeded.
So this is much more different. They are difficult. They have to arrive at the almost same time or within certain window.
Yeah, if they do not arrive, then they become noisy, and then entanglement swap will not succeed.
Okay.
And then so there comes the challenge basically. So the repeat until success framework, which was basically previously introduced in discrete time. Basically, we try to do it So this slide. I should do it in the style. So basically, we do some generation first, and then we make some measurement, and then we communicate the result. That is the framework. Basically, under this framework, many primitives of computation can be found. So what we are trying to say here that the durations are not only deciding factors, but they could be hidden variables, which actually describes the success or failure of the measurement. And using that, you can actually find the total duration of the time until success. So and I think this is the last slide I'm going to.
But this calculation scheduling, this seems more in the classical world than in the quantum world, right? Because this.
I mean the durations are like.
But these are just random variable calculations.
Yeah, exactly. So I mean I just have to model the experiments and their success and failure.
Okay.
And then what I'm trying to come up here with is I find the MGF and then find the MGF for the total duration and success, and then I just use Chernow's form. And if I want better bounds, I can probably use Brown's bound, which is on a bound that it's an approximation, and so on. And the real example that I want to show is about quantum distribution, where it is actually made up of minuscule steps. And each step is.
See, if you want to present this stuff, you didn't have to talk anything about quantum. You could have just directly went to the problem and just abstracted it out. But good that you taught us quantum, but if you really want to present this, all of quantum can be ignored, right? You can just say that it will be Fourier and
not
in this
not really. I think not really because because I mean, first of all, I did not assume that people have quantum background here.
No. So even I don't, but I would have believed you if you said that you need to be within a certain bound, and you can just a random process question you could have asked, right? And then we would be okay with.
No, I mean, I just wanted to explain why.
No, this you would not have understood. That you're too ambitious, I think.
I think I just wanted to. And this is the crux of the thing that I want to present. But
see. My apologies.
No problem.
Most quantum talks happen like that. Our term does quantum coding. It's just to explain the background, it takes too much time. Non-expert. So I think you should go there. I think you have more. This will not happen.
No, I already said it.
Okay. Thanks. It's time to speak.
So there are other questions. Yes. Oh,
you can stop it.
Thank you, Dr. Sounak, for a great talk. We can take a few more questions. Okay, thank you, everyone. Please go ahead.